So we will have what you call A11 into C11, where the coefficient of A11 is the smaller determinant. Uh, that is, the coefficient of A11 is the smaller determinant with row 1 and column 1 removed. So what he is telling you is, if you take this over here, then this A11 has to be multiplied with the determinant here. Then this A12 is to be multiplied with the determinant, leaving this column and this row. That means determinant which consists of these two elements and these two elements. The third one will be this multiplied with the determinant formed by this here. So A11 and the cofactor corresponding to that, A12 and the cofactor corresponding to this and this, A13 and the cofactor corresponding to this and this. So, and that's what is written over here, A11 and C1. So cofactor of A11 is C11 equal to sigma. If you take any, general, n by n matrix, then it will be the summation of A2 beta, similarly A3 gamma, and so on till ANV. So determinant of multiplied by the determinant of P. And determinant of P, as I said, can be either plus or minus 1. So it just gives us the determinant of the submatrix of A. This will be the, C11 will be the submatrix of A. Cofactor of A11 will be the determinant of the submatrix of A. Similarly, the entry A12 is to be multiplied by C12, and grouping all the terms that start with the same A1j, it becomes the cofactor along row 1. That is, determinant of A is equal to A11 C11 plus A12 C12 plus dot 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 plus A1n C1n. So this shows that the determinant A depends linearly on the entries A11 to A1n of the first row. So we can take an example of a 3 by 3 matrix where determinant of A we know very well, A11 multiplied by this is the one which is referring to the cofactor of A11, and that is nothing but the solution of, if you just take go back there, which is nothing but this itself. That means if I take this over here, then A11 multiplied by A22 into this minus of the multiplication of these two, and that's what is written there. Similarly, A12 multiplied by the value A23, A31 minus A21, A33, and that is what is written over here, this one. Similarly, this one. So all those three terms are there over here. The cofactors C11, C12, and C13 are the 2 by 2 determinants in the parenthesis. So that is what is a sub determinant of a submatrix. Submatrix means earlier we had 3 by 3, the cofactor will be 2 by 2. If earlier it is n by n, then the cofactor will be n minus 1 and n minus 1. And you should go down like that, in that way. So expansion of the determinant A in cofactors is what need to be done. C1j depends on the row 2 to n. Row 1 is already accounted for by the A1j, and then we need to consider the rest of the terms as C1j. Furthermore, A1j also accounts for the jth column, so its cofactor C1j must depend entirely on the other columns. It cannot depend upon that column. So no row or column can be used twice in the same term. We cannot use the same row and same column twice in the same term. It will be, one row, next row, and the third row always. For example, first term will be A11 into A22 into A33. So you're using first row, second row, third. Then second term might be A11 into minus of A23 into A32. So that will give us the value which will be, first row, second row, and third row. Similarly, all the others also will be like that. So for a determinant of order n, this splitting gives n smaller determinants or minors of order n minus 1. The submatrix M1J is formed by throwing away row 1 and column J. Just trying to describe the process of how we can find the value of the determinant. So its determinant is multiplied by A1J and by a plus or minus sign. These signs alternate as in the determinant M11 minus determinant M12, determinant M13. So if you take the sum of this 1 plus 1, if it is even, then we will have a positive coefficient. If the sum of this is odd, we will have a negative coefficient. Again, the sum of this is positive, you will have a positive coefficient. So thus, the cofactors of row 1 will be C1j is equal to minus 1 to the power 1 plus j, determinant of M1J. M1J is the sub matrix which we have. So the second cofactor C12 is A23 multiplied by A31 minus A21 into A33, which is the determinant M12 times the minus 1. So this same technique works on every n by n matrix. The splitting above confirms that C11 is the determinant of the lower right corner M11, and there is a similar expansion on any other row, say row I. It could be proved by exchanging row I with row 1. So you can always, exchange the row 1 with row I and consider that the expansion is similar to whatever we have done here. So we always see that we delete the row I and column J to get the value of Mij. To get the submatrix, we delete the row I and column J. That means in the earlier case, if you just see over here, okay, this is the submatrix, and this is got by deleting this and this column and row. Okay, this column and this row. If you delete, we will get this term, and that is what is written over here. Similarly, this is to be multiplied by this over here. So the sub, matrix is the matrix 2 by 2 with these elements, right? So for that, what do? We delete this row and this column. Similarly here, A13 is there here. To consider this, we delete this column and this row, and we'll get the submatrix here, which is same thing as this over here. So we delete the row I and column J of A to get the Mij, to get the submatrix. So the determinant A is a combination of the determinant determinant of A is a combination of any row I times its cofactors. Determinant A by cofactors will be determinant A is equal to AI1 CI1 plus AI2 CI2 plus etc. AIN CIN. So this is the way to compute the determinant of A using the cofactors. So the cofactor C1j is the determinant of the submatrix Mij with the correct sign, whose formula can be written, the what we callCij's over here can be written like this: minus 1 to the power I plus j, determinant Mij. So that's what I said. If we add these two, then if it is odd, then you'll have a minus term here. If it is even, then you'll have a plus term here. So that's why we have written minus 1 to the power I plus j. So these formulas express the determinant A as a combination of the determinants of the order n minus 1. There is also one more consequence of this, and that is determinant of A will be equal to the determinant of A transpose. This is very much true. Determinant of A will be equal to determinant of A transpose. It is just by exchanging the columns and rows, we will get this. We can expand in cofactors of a column of A, which is a row of 80. So how do we get the transpose? By exchanging the rows and the columns, by exchanging the rows of the columns. And in that case, you will get the formula like this. compared to this. So here we are fixing I, here we are fixing J. Okay, we are fixing the second, so to say. Here we are fixing the, you know, first value here, that is the row value here. We are fixing here the column value J, 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 J. Everywhere you can see that J is appearing, and J is the second term, which just corresponds to the number of columns. Here we are fixing the number of rows, I, and all. So we can take an example here. The 4 by 4 second difference matrix A4 has only two non-zeros in row 1. This is a second difference matrix which is 4 by 4. 2 and minus 1, 0, 0, minus 1, 2, minus 1, 0, 0, minus 1, 2, minus 1, 0, 0, minus 1, 2. So you can see that these two terms are 0. So corresponding to this two terms, you will get the expansion, which will be just, you know, of no consequence, because 0 multiplied by the submatrix will give us the value equal to 0 itself. So only this and this term have to be multiplied with the submatrix. So this term should be multiplied with the submatrix, which is leaving this column and leaving this row. That means this total thing. Okay, this total thing. So this will become the cofactor corresponding to this two. Similarly, for minus 1, the cofactor will be this column, this row, and this column should be left. That means these three elements, these three elements, and these three elements will together become the submatrix corresponding to that. So C11 comes from erasing row 1 and column 1, row 1 and column 1, which leaves the pattern minus 1, 2, minus 1 pattern there. And that will give us C11 is equal to determinant A3 equal to the determinant corresponding to this one. Similarly, for A12, we'll have the minus 1, A12 equal to minus 1, which is there over here. It is the column 2 that gets removed, and row 1 is definitely there, and column 2 which will get removed, and we need its cofactor C12, and C12 is this and this and this together. So C12 will be minus 1 to the power 1 plus 2, determinant of, you know, those three columns which I just said, and that you can try to solve as this, and that will become the determinant of A2. So altogether, row 1 has produced 2 C11 minus C12. 2 into C11 minus, the coefficient of C11 is 2 in the problem. This is only for the specific problem of the 4 by 4, you know, second difference matrix, which is mentioned over here. And for that, the value is 2 into C11 minus the coefficient of the C12 is minus 1 over there here. So this multiplied by C11, this multiplied by C12 is what we have over here. And thus you can just write that determinant of A4 is equal to 2 times of determinant of A3 minus determinant of A2, and determinant of A3 is 4, determinant of A2 is 3, and you can just substitute and you get the value of 5. So the same idea applies to A5 and A4 and every AN. Recursion by cofactors, we can always write. So if you go on writing in that way, for the again second n by n, you know, so to say, second difference matrix, n by n second difference matrix, then the recursion by cofactors will just correspond to determinant an equal to 2, determinant an minus 1, minus again determinant an minus 2. So this gives the determinant of increasingly bigger matrices. At every step, the determinant of an is n plus 1 from the previous determinants n and n minus 1. So for a minus 1, 2, minus 1 matrix, determinant of an is equal to 2 into n minus 1 is equal to n plus 1. So the answer n plus 1 agrees with the product of the pivots which we have discussed till now. That means when we consider the example, you know, there in case of yes, this value over here, this is again a second difference matrix. So this can be any n by n matrix. In that case, say if it is 4 by 4, then we will have 4 terms: 2, 3 by 2, 4 by 3, 5 by 4. So if you multiply all that, 2, 2 cancels here, 3, 3 cancels here, 4, 4 also will cancel. We are left with 5. And 5 is nothing but n plus 1. So if you multiply all this, you will just get n plus 1. And that n plus 1 is what is again proved, in the example considered there. In the, example considered here, n plus 1. So there are a number of applications of determinant, and one is the computation of A inverse. You can compute the A inverse. So A is written like this, and if you take that, then naturally you know how to get the A inverse. That is this term divided by the determinant of the matrix, which is A, B, C, D, and 1 by determinant of A. And here we write the C11, C21, C12, C22. The number C11 is D, is a cofactor of A, and C12 is minus C, the cofactor of B, and so that means we write a cofactor matrix divided by the determinant of A, and then we'll get the inverse. So that's the process. So A inverse divide the cofactors by the determinant of A. So A inverse is cofactors divided by the determinant of A. C transpose is the way in which the cofactors are written. You can see that C11, and we should have written C12, and then C21, C22 transpose, and that is what is C over here. C is C11, C12, C21, C22 written in a proper way. Transpose of that will be this quantity. So means that again A inverse Ij is equal to Cij divided by determinant of A. So Ij here and Ji will just give us the transpose quantity. So again we can write the same thing in this way. You can just exchange this over here and write it. This you can take it this side, this you can take it this side. Then you'll get Ct by A inverse. 1 by A inverse will just give us the value A. So then R, you can multiply both the sides by what you call A here. If you multiply both the sides by A over here, if you multiply this by A on both the sides, A inverse will be I, and here you will be left with ACT divided by determinant of A. If you cross multiply I into determinant of A will give ACT, and that is what is written over here. ACT is equal to determinant of A into I, and if you multiply any determinant with a I value, so it doesn't change the value, you'll get just determinant. So A we are writing here, C we are writing the C transpose we are writing here, and then that is equal to the determinant A at all the places in the matrix. So the solution of AX equal to B is what is the second example which we have. First is the computation of A inverse. The determinant can be found to get the solution of AX equal to B. So this will be, AX will be, if A is invertible, then we know that it will be A inverse of B is just the CTB divided by the determinant of A. The CTB divided by the determinant of A will give us the value of X. So you can apply the Cramer's rule. The Cramer's rule standard we know, which again corresponds to that only. The jth component of X is equal to A inverse B is the ratio. Xj will be equal to determinant of Bj divided by determinant of A. This is the Cramer's rule, where Bj is just this, wherein what we have done is we have the B in the column J. B we have written in the column J, and that is what is Bj. So an example is considered over here. X1 plus 3x2 is equal to 0, and 2. We have tried to apply the Cramer's rule and tried to solve the numerical. Standard Cramer's rule, we know very well how to find that. So with this, we come to the end of the chapter here. So I'll take a numerical for your doubt, because you are not able to get, I think, whatever is there in this